This is a new section from Planar Kinematics of a Rigid Body, 16.5, Relative Motion Analysis for Velocity. And it has to do with similar type of problems that we solved using absolute motion, where position is given, and we have enough information to where we can, you'll see, complete a vector loop formed with velocity vectors. So what we're looking at here is a body, looks like a bar AB, and we know the motion of A, and we're going to study the motion that is velocity, this time position velocity for point B, and there's this translating reference frame. So x-axis ax prime remains parallel to OX, and if you look at this angle and we call it theta, this angle measures the orientation of the line AB, and as this angle changes, there's rotation that's overlapped with the translation of body AB as point A moves in plane. So point A performs some path reference frame, x prime A, y prime remains, keeps orientation, the axes remain parallel with those of the fixed frame, and we can say this this vector equation. So position vector of point B is going to be position vector of point A, which we assume known, plus position vector of B with respect to A, the third term, or second term to the right of the equal sign. We can take now displacements of the vectors, the position vectors, and they can be infinitesimally small, that is happening in a small increase of time. And initial position, we have it here to the left, and A goes to A prime, I could call it, B goes to B prime. These are the changes in vectors of a vector RA, a vector RB. And we can assume that the second, going from the first position to the second position, happened as a translation. Okay, you can see it here in dashed line, and then a rotation by the angle d theta. Okay, and the corresponding vector equation from before, when it comes to infinitesimal displacement, gets is of this type, where the change in the relative position, that is vector r of B with respect to A, is due to the rotation due to d theta. Without it, there's dr B would be equal to dra. Okay, so if there is no rotation, this vector is 0. It means that these two vectors are identical. I said that velocity interests us, so dividing by the corresponding time increase, the early equation, the displacement equation, we get to where we recognize this as being the absolute velocity of point B. This is the absolute velocity of point A, and this is the velocity of, we'll call it velocity of B with respect to A. And we've been here before when we studied curvilinear motion of particles. So the last term in this equation, drb with respect to a over dt, is going to be equal to, or maybe here, the position vector of b with respect to a times the time derivative of angle theta, which is the angular velocity of the link. Okay, so angular velocity, the time derivative of theta. There was never a mentioning on how this angle theta is measured. We were looking only at increases in theta and or changes in theta. And if they are counterclockwise, they are assumed positive. Okay, so this is one important equation that is repeated here. That is velocity of point B is velocity of point A plus velocity of B with respect to A. Okay, so in summary, the general plane motion of a body like this one, slender AB, is going to be a translation. That is, the line AB remains parallel to itself, and we know the translation of a reference point on the body, that is point A, to which we are adding a rotation of the body about point A with the angular velocity omega. So the velocity, the absolute velocity vector, is going to be the sum of these two velocity vectors. In this part of figure 16, we see the vector equation written, so it's a triangular loop. We have velocity of B is velocity of A plus velocity of B with respect to A. So this is a closed vector loop, and useful in solving a number of problems. Another way of stating the early equation is to explicit what the velocity of B with respect to A is. It's the cross product between the angular velocity vector, which is a vector that is parallel to the z-axis and positive if we discussed this already. So it's positive if omega is counterclockwise. So this would be a negative omega as is shown oriented here. So positive would be counterclockwise. Multiply or crossed with position vector starting at A and pointing to B. Okay, and we can work with the scalar components and calculate the angular velocity by multiplying the omega vector if known with r of B with respect to A. Here's an example. We have a slider crank mechanism, and position should be given. Here's the angle 45 degrees. This is a single degree of freedom mechanism, so motion is specified by just one input. I can either rotate a crank, move the piston, or you could even drive, say by hand, the connecting rod AB. But assuming input from the crank, like in piston compressors, and assuming a positive angular velocity that is to the left, then for a given position, that is crank angle 45 as shown here, we can state a vector equation like this one, where it allows us to calculate the velocity of point A. The velocity of point B, if we know omega and length CB, so velocity of B, it can be calculated in terms of its orientation. It's perpendicular to the line BC. Okay, so it's perpendicular. We have 90-degree angle here, and then its magnitude is going to be length CB times omega of BC. Okay, so that's one. So velocity of B, and then about velocity of A, we don't know angular velocity of link AB. We could find it, but what we know is the direction of velocity of A, that is a horizontal line. So you see it here, and we can state the equation like before. So with this term being velocity of, well, we have B. So let me just say velocity of, will be the easy way of doing it. So if we go from B to A, then I need to say absolute velocity of A is absolute velocity of B, which you already got it, velocity vector. So velocity of B plus relative velocity of A with respect to B. All these being vectors. Okay, vector, vector, and vector. And I said that we know the velocity of B. Velocity of B with respect to A will have a known direction, so it's like rotation of the body AB relative to B. So velocity of AB, A with respect to B has this direction, perpendicular to line AB. And then this other velocity of A, we know it has a horizontal direction. It's not the happiest choice. It might be confusing to the student, so it's only accidentally that link AB is horizontal. It could have taken an angle other than 45 degrees to where this becomes a bit more general, or more general. Okay, so in a two-dimensional vector equation, or two-dimensional vector equation equivalent to two scalar equations, so we can leave with two unknowns, or we can handle and solve for two unknowns. In a vector equation, if it's a triangular vector equation, if we know the one of the vectors, which is B, and the direction of the other two, problem is solved because it's equivalent to resolving the given vector about two given directions. So I can restate this equation to where velocity of B is velocity of A minus velocity of A with respect to B. I know the two directions, so again it's equivalent to resolving vector B about one direction that is perpendicular to link AB and the other one that's a horizontal line. Another example here shown is where a wheel rolls without slip on a flat surface. Velocity of A, point A, contact point is 0. If we know omega, we can find velocity of B. It'll just be velocity of B is velocity of A, which is 0, plus relative velocity of point B with respect to A, which is radius of the wheel times omega, and has the direction that is perpendicular to the line AB, and has the direction of omega. So if omega is clockwise, velocity will be to the right. A summary of or procedure for analysis. And so we need to have the position problems fully defined. We need to know link length. We need to know an input position, like you saw earlier. We had an angle for for a problem like this, wheel is rolling without slip is not of relevance to know like what point is this relative to, say, a Mark spoke, or so not all problems, but some linkage types, we need to know an input value to work and draw the mechanism and perform the velocity analysis. Okay, so everything revolves about this equation or its companion, which is this one. And you can either perform calculations and write the equivalent scalar equation and evaluate this cross product, find the x and y components of the relative velocity, or you work it graphically. All right, so there are some examples here, and let's go to the next one, and then we'll come back. Why is that? Because this is a more straightforward application of the relative velocity equation. So we have it here stated, and we're given a conveyor belt, and the belt moves to the right at this velocity. And then we have a disc that rolls without slip on the conveyor belt with this angular velocity, and the angular velocity is negative, rotates the body to the right. So question is, what's the velocity of point A? And velocity of A is velocity of B plus velocity of A with respect to B. And so we can we know already the velocity of B. It's the velocity of C. It's a horizontal, no magnitude, horizontal and to the right. And then to evaluate this cross product, we know the omega. It's a we know its magnitude. It's 15 times k, the unit vector associated with the z-axis, and then position vector of A with respect to B, okay, relative to the fixed frame, has negative 0.5 times I plus positive 0.5 times J component. So this is the cross product, and we're going to simplify it and collect the terms in I and J, and so we're going to equate terms. So velocity of A over the x-axis is going to be 2 plus 7.5, that is 9.5 feet per second, and then in the J direction, the y direction, y-axis direction, is going to be 7.5. Okay, so these are the x and y components, velocity of A, and then to get the magnitude, we apply Pythagoras theorem, and to get this angle that orients the velocity vector, they could have used a different symbol rather than theta. Theta, usually we use it to show like theta being the original position angle that from where omega is coming. Anyway, so they use theta as a orientation vector, and we can get it by stating the tangent of the angle theta is going to be the y component of velocity, absolute velocity of A over x component. Okay, and it's 38.3 degrees as shown here. Again, angles should be oriented. I keep on saying that. Okay, now instead of going through these steps, we can apply more geometry. So we can use the vector equation in this form, and we know the direction of velocity of B, and then we know, which is a horizontal vector, I know the velocity of b with respect to a. It's a vector that's perpendicular to line AB. Okay, so if it's perpendicular to line AB, if this is so going back to the original, so if this is 45, this will be 45. This other one is also 45. So a line that's perpendicular to line AB would be at 45 from the horizontal. So this velocity of A with respect to B. And we can calculate it. Is going to be distance AB times omega, and has the direction of omega. So has the direction of omega. Okay, so we can now write the velocity of x and velocity of y. Rather, velocity of A was along the x-axis, along the y-axis, by projecting the vector equation that's boxed here. So I have the velocity of B does not have a y component. It's magnitude 2 and positive to the x-axis, and then you look at the velocity of B with respect to A. I have so by multiplying 15 radians per second with this distance, so the distance AB is going to be what? 0.5 square root of 2. All right, so I have 0.5 square plus 0.5 square. Square root is 0.5 square root of 2, or I can say AB is equal to square root of 2 over 2, which happens to be the same as sine of 45, or the same as cosine of 45. I don't know why sometimes problems are could be confusing just because they are not the most general formulation possible. Okay, so we have magnitude of B multiplied by 15. This is the magnitude of velocity of A with respect to B. And we can project it over X and Y. And we find number that we saw before. Okay. So it's confirmed. And then from there, we can calculate the absolute or magnitude of the absolute velocity using the same equation. And angle likewise. Same approach. Let's go back to problem 6. So here, what we have is a link that is guided with one end about a vertical axis, and with another point, a distance 0.2 meters from A, along the horizontal axis. There is an input given and a position given. So when the angle is 45 degrees, we want to find velocity of B, and using relative motion analysis. Okay, so here's a fixed reference frame. In the vector equation, that I use it in this form, relative velocity vector equation. We're in this form. So we have velocity of A that's fully known. We don't know omega, but we know the vector position vector are B, A, B slash A, position vector of B with respect to A, as magnitude is 0.2, and also as components, because we have so 45 degrees. So this the x component will be 0.2 times sine of 45, and the y component is negative. Again, vector goes from A to B, so projects as a positive scalar over the x-axis and a negative scalar over the y-axis. Okay, and the omega is not known, but we definitely know which direction the relative velocity is going to have, and that's going to be perpendicular to the line AB or ABC. Okay. So we state this equation, and we explicit terms, and notice that they have just the velocity of A just or J component, a velocity of B just I component, and we write them, value the cross product with a unknown omega, and then equate terms I with I and J with J, and allows us to calculate the omega, and allows us to calculate the magnitude velocity of point B. Okay. If we're to do it in scalar analysis instead, we have so this is the companion alternative form of this other equation, and it will be a matter of knowing that the velocity of B with respect to A projects with equal magnitudes and both positive over X and Y. We can write a vector, the actual vector loop equation, so I can say, in drawing at scale, I'm trying to draw a straight line down, so I have velocity of A, okay, velocity of A plus velocity of B with respect to A, and that's has this direction. So I'm trying to copy this direction and draw it here. And I need to extend this, sorry. Okay, this continues, and then I know I need to close the vector loop with a line that's horizontal. So I have velocity of, and this should have been capital A, velocity of A plus velocity of B with respect to A equals velocity of B. Okay. So resolving the velocity of A vector, this can be moved on the fly. So velocity of A, you resolve it about two directions, one that is horizontal and one that is at 45 degrees. So this is 45 degrees, and of course this is also 45 degrees. Okay. There are additional problems. So there's this one, 16.8, and what do we have? We have a color. This is the last one of the solved problems, and color C is moving down with the velocity is given, and we need to find the angular velocity of CB at this instant. Now we can only assume it's not specified, or it's not explicit, but we can assume that this angle is 90 degrees, which doesn't make the problem most general, but it definitely will be a simplifying case. And we're given the distance, so AB appears to be 0.2, and then at length BC is going to be square root of 2 times 0.2. So yet again at 45 degree angles, and let me move this to where you can see the full page, or the page. And this other one will also be 45 degrees. 45. Okay. So we write the equation, relative velocity equation, and we know the input it's parallel to the y-axis and in the negative direction, and we know the magnitude 2 meters per second. So that's velocity of c. Okay, so in order to find omega of CB, we need to state the relative velocity equation for point B. And we know the direction of velocity of B is going to be a line that's perpendicular to AB. Okay. And then we know the relative velocity of B with respect to C, and that's a line that is perpendicular to, like shown here, perpendicular to the link CB. So nothing more easier to, I would say, very much the same as the earlier one, problem 16.6. Omega again is unknown, but we know the position vector of RB with respect to C, so has a positive 0.2 component, negative 0.2 component over y-axis. This is it, and then velocity of C has only a y component, velocity of B has only an x component, and you equate or put together, combine what's multiplied by I unit vector, combine what's multiplied by j unit vector, and so it would be enough to solve for the two unknowns, which are the omega and the magnitude of omega and magnitude of the velocity of B, or yes, of B. So the two unknowns here, they are solved. The scalar approach, here's where I would always draw the vector, triangular vector loop. But you would, so going with this equation, clearly velocity of B is has just horizontal component. Velocity of C is known fully. It's only a vertical component. Velocity of B with respect to C, it's somewhere along a line that is 45 degrees. And you extend the, continue calculations, and you could even, as I'm looking here, you can even calculate omega of a link AB, of the output link. Okay, so I guess this is it. There are some problems, and you will see the type of problem that we will solve. They have some limitations. So the velocity vector would have to be a triangular loop. Okay, so in this case, with inputs being the shown link of 2 meter long, and this appears to be 90 degrees. It's not specified. Here appears, it's not specified, but it's assumed horizontal. So some simplifying assumptions. Not that other more arbitrary position could not be tackled, but will be a little bit more involved. Okay. All right. So this is it. I'm going to solve some problems in class, and recording stops here. Thanks for watching.